Throughout the 1920s, the bizarre predictions of quantum mechanics generated significant debate, most famously between Albert Einstein and Niels Bohr, who was at the head of the Copenhagen interpretation of quantum theory. Einstein disliked the concept of uncertainty inherent in quantum theory, but whenever he challenged Bohr, Bohr always managed to find a flaw in Einstein's proposed experiment using some semi-classical counterargument. However, in 1935, Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, hence the name EPR, wrote a paper entitled Can Quantum Mechanical Description of Physical Reality Be Considered Complete? Up to this point, all debate had been focused on a one-particle system, but EPR presented a thought experiment involving an entangled two-particle system, which brought up a phenomenon that quantum mechanics correctly predicted but couldn't seem to explain. In order to understand that argument, however, we first need to address the idea of quantum entanglement. Entanglement describes a fundamental correlation between two objects. Consider, for example, two identical twin kittens, Augustus and Ben, who can each be either awake or asleep. If the kittens are apart, say in different rooms of a house separated by a wall, then there are four states we could find the two-kitten system in: Augustus awake and Ben asleep, Ben awake and Augustus asleep, both awake or both asleep. However, if the kittens are together, then when one is awake it will automatically wake its sibling up, while if one is asleep the other will doze off with it. Hence, the two-kitten system has been reduced from 4 to 2 possible states, both awake or both asleep, meaning that we can deduce the state of Ben just by checking the state of Augustus, and vice versa. We would say that, in this setup, the two kittens are, as coined later by Schrödinger, Verschränkung, or entangled. Note that the theme of sleep-talking cats will not play a major part in this video. Now, let's take a look at a variant of the thought experiment proposed by EPR, with Augustus and Ben, who have been well-behaved, as our observers. EPR considered two physical systems. In the kitten example, the cats were the two systems, but here we'll use photons, which we'll call A and B. They are said to possess two non-commuting variables which, according to Heisenberg's uncertainty principle, cannot simultaneously have definite values for a given system. We'll say x spin and y spin, the values of which can either be up or down, as shown here. The original paper considered position and momentum of two electrons, but the quantum phenomenon we'll observe is the same with photons and spin. Now, to make sure our photons are entangled, we need to prepare them specially. Let's say that they are formed back-to-back from a neutral pion at rest. The pair of photons is therefore described by a single two-particle wave function. These photons are then separated until they are no longer linked in the traditional sense of local coupling, but they're still described by the same wave function. And at this point, Augustus measures the x-spin of photon A and finds it to be up. It doesn't actually matter whether it's up or down, since both are equally likely, but we'll stick with up. Ben can now deduce that photon B's x-spin is down, since the total angular momentum of the final two-photon system must be the same as that of the initial state, the resting pion, which had zero angular momentum. Now, imagine that Ben then measures the y-spin of photon B and finds it to be up. Something must be wrong here, since Ben now knows both the x-spin and the y-spin of photon B, which is more than the Heisenberg uncertainty principle allows. Remember that x and y spin are non-commuting variables, so you can't know both with certainty for one photon. Was Heisenberg just wrong then? Well, no, he wasn't. But this brings us to another problem. Going back to the experiment, it turns out that once Augustus has measured the x-spin of photon A, not only can Augustus not measure A's y-spin, but Ben also can't measure photon B's y-spin. This means that the uncertainty principle is not circumvented, but it also suggests that photon B instantaneously knows that a measurement has been performed on A. From now on, we'll call this strange phenomenon the entanglement effect, but the crucial question is, how does this effect arise? How does photon B seemingly immediately know what's going on with photon A? Well, EPR offered two explanations, one which they thought created a paradox, and the other which they thought the only sensible option. First, we could accept, as quantum theory seems to suggest, that there was some instantaneous communication between the particles even though they were separated. However, since the particles could be light years apart, whatever information travels between them when Augustus measures the x-spin of photon A must travel faster than the speed of light, which violates the universal speed limit set by special relativity. This brings us to the heart of the paradox. How does photon B know what's going on with photon A, despite the fact that this seems to violate special relativity? This concept of faster than light communication is what Einstein famously labeled spooky action at a distance, and it's what brought EPR to claim that quantum mechanics was incomplete. To remedy the paradox, EPR suggested that we reject such spookiness, leaving the only alternative explanation that somehow, when the particles were created, they had some hidden variables embedded within them that govern their behavior such that they always act in a complementary way. This would imply that information about the outcome of all possible measurements was already present in both particles, a phenomenon which is not observed by quantum mechanics, suggesting therefore that the quantum model of reality is incomplete. This theory, favored by EPR, is known as a local hidden variable theory, where local means that measurements and interactions at one point in space can only instantaneously affect measurements in the immediate neighborhood, and all other information transfer must occur at a speed equal to or less than that of light. Spooky action at a distance, by contrast, implies non-locality, which Einstein took issue with. Now, it's important to quickly go through the basic logic of the EPR argument again, since it doesn't come across as clearly from the paper as Einstein wanted. First, EPR assumed that a non-local explanation of the entanglement effect was impossible, since it would imply faster than light communication. Hence, the explanation of the effect must be a local one. Third, the only possible local explanation is one where we assume hidden variables in the particles, since this is the only way they could be perfectly anticorrelated all the time without communicating with each other. Hence, EPR adopted a local hidden variable theory as an explanation for the entanglement effect. Fourth, in a local hidden variable theory, particles have simultaneous reality before they are measured. This is not predicted by quantum mechanics, which states that all particles are in a superposition of different possible realities until measured. Hence, quantum mechanics is not a complete description of reality. Oh, and one more crucial assumption was that the predictions that quantum mechanics gives for the entanglement effect are correct. That the entanglement effect is what happens when two particles interact and are then observed in such a way as we have shown. This assumption, along with the assumption that non-locality is impossible, provides the foundation for the overall argument that quantum mechanics is an incomplete description of reality. Now, of course, Bohr didn't like this very much. However, EPR's argument couldn't be dismissed by Bohr as easily as before, because EPR had hit upon the crucial difference between quantum mechanics and all of classical physics. Quantum mechanics is a non-local theory, and no semi-classical counterargument could explain the entanglement effect, which is at the heart of quantum mechanical non-locality. We'll touch back on this major point later. The debate between non-locality and locality therefore brought quantum mechanics to a philosophical brick wall. Those who supported quantum theory were unconvinced by the EPR argument, but could not think up a satisfying counterargument. Meanwhile, supporters of EPR were bothered by the implications of spooky action at a distance, and how quantum mechanics nonetheless seemed to make such accurate predictions about properties of the atom. What both sides lacked was a definitive experiment to bring the debate back from pure philosophy to testable, falsifiable science. After almost 30 years, in 1964, this is exactly what Northern Irish physicist John Bell came up with in his paper on the Einstein-Podolsky-Rosen paradox, a definitive way to test whether or not a local hidden variable theory could explain the entanglement effect. It was in this paper that the famous Bell's inequality was derived, and we'll derive a variant of it here. Imagine, first of all, that we have two entangled photons, A and B, that are sent to two different photon detectors, A and B respectively. Of course, the photons are identical, so it's arbitrary which is A and which is B, but we'll label them for the sake of clarity. These photon detectors have slits at three different angles which measure whether the photon spins are up or down. If the photons go through the slits, we say they have spin up. If not, they have spin down. The exact angles are unimportant since they are merely relative to one another, so we'll use three angles 120 degrees apart to keep things neat. Now, if we were to compare the predictions of a local hidden variable theory and quantum theory, we would see that the probability of the two photons giving different spins for the same angles measured on each detector is the same according to both theories. This makes sense because one thing that we know for certain is that the two photons are always anti-correlated for a given measurement, so this is worked into both theories. However, we can also look at the probability that the detectors give different spins for the photons measured at different angles. This probability, let's call it little p, is different for a local hidden variable theory than for quantum theory. So, by finding what a local hidden variable theory predicts and then seeing what the experiment shows, we can tell whether a local hidden variable theory can explain the entanglement effect after all or not. First, let's look at the predictions that any local hidden variable theory would make. Since all the possible outcomes to the experiment are already encoded in the particles, we can simply list all the ways in which the two particles can have different spins at different angles. There are two possible plans, if you like, to give all the combinations of different spins at different angles. The first plan involves photon A getting spin up for all three angles. In this case, photon B must get spin down for all angles, since the photons always have anti-correlated measurements for the same angle. Hence, there are 6 combinations of different angles, of which all 6 give different results. So, little p for plan 1 equals 1. Now on to plan 2, in which photon A has spin up for 2 angles and spin down for the third. Hence, photon B has spin down for 2 angles and spin up for the third, giving a total of 2 different spins at different angles out of 6 combinations. So, little p for plan 2 equals 1/3. All other plans are mathematically equivalent to the two above, since the order of spins up and down is unimportant, and it's arbitrary as to which photon is A and which is B because they're identical. Hence, overall, a local hidden variable theory predicts that little p is greater than 1/3 and less than or equal to 1. This is a variant of what is known as Bell's inequality. Now, onto what quantum theory predicts. Again, we have 2 scenarios to consider, although we can't call them plans as they aren't pre-prepared. They're just different possible ways in which the photons could have different spins when measured at different angles. In the first scenario, photon A has spin up for one of the angles. Hence, photon B has spin down for that same angle. Now, the probability photon B has spin down for either of the other angles is equal to sine squared of 60, which is 0.75. Let's take a quick detour to explain why. We can take a standard Cartesian grid and plot the result that we already have for photon B, which is spin down for angle 1. Now, let's consider whether or not the photon will go through the slit at angle 2, i.e. whether or not it has spin up at angle 2. We can split this spin, which we can think of as a vector of magnitude 1, into 2 components. One represents spin up for angle 2 and is at 60 degrees from B's spin vector. The other represents spin down for angle 2. These form a right-angled triangle with the spin vector. Hence, the vector representing a spin up at angle 2 equals cosine 60, and the vector representing spin down at angle 2 equals sine 60. The intensity of the photon's field is proportional to the square of its amplitude. So, if we think of magnitude on our diagram as amplitude, we see that the spin up intensity is proportional to cos squared 60, and the spin down intensity is proportional to sine squared 60. Hence, the probability of spin up for angle 2 is equal to cos squared 60, which is 0.25, and the probability of spin down for angle 2 is sine squared 60, which is 0.75. The same applies to the third quadrant for angle 3. Returning to the detectors, hopefully it now makes a bit more sense as to where those probabilities come from. In the second scenario, photon A has spin down for one of the angles. If we follow the same reasoning through as for the first scenario, we find that the probability of photon B having spin up at angle 2 or 3 is equal to sine squared 60, which is 0.75. These are all the possible combinations we need to consider. So, overall, quantum theory predicts that little p is equal to 2 times the probability that photon A is measured at a given angle, which is 1/3 because each angle is equally likely to be chosen and there are 3 of them, multiplied by the probability that A's spin is up at that angle, which is a half because spin up and spin down are equally likely, multiplied by the probability that B is measured at a different angle to A, which is 2/3, 1/3 plus 1/3 because there are 2 other angles to choose from and each is chosen with probability a third, multiplied by the probability that the spin of B is down at either of those angles, which is 0.75 as we've shown. And by the way, we multiplied by 2 at the beginning to include the second scenario where photon A has spin down at the angle it was measured at. So that's 2 times a third times a half times 2/3 times 3/4, which is 1/6. So to recap, any local hidden variable theory predicts that little p is greater than 1/3 and less than or equal to 1, whereas quantum theory predicts that little p is equal to 1/6. Experiments carried out in the late 1970s and early 1980s showed that indeed the relative frequency of different spins at different angles for the different photons over billions of trials with billions of pairs of entangled photons was 1/6. Since this is less than 1/3, the minimum value permitted by any local hidden variable theory, we say that the experiment violates Bell's inequality. It shows that no local hidden variable theory can explain the predictions made by quantum mechanics concerning entangled particles, whereas the theory of quantum mechanics as it stands explains the phenomenon well. Now, experiments aren't perfect, and as such, the early tests had many loopholes which meant that local hidden variable theories couldn't be entirely ruled out. However, these loopholes have been almost entirely addressed as technology has advanced, so most physicists today agree on the true outcome of the experiments. So, what does all of this actually mean for quantum physics and for our understanding of the universe in general? Alan Aspect, who was at the head of the definitive experiments that violated Bell's inequality in the 1980s, put it nicely in an article in Nature magazine in 1999, in which he wrote that a pair of entangled photons must be considered a single non-separable object. It is impossible to assign local physical reality to each photon. This basically means that it is impossible to explain the entanglement effect using the physics of locality. One photon cannot really be said to exist in space without taking into account the other photon. One important thing to remember, however, is that we can only make a conclusion about locality, not about hidden variables based on Bell's experiment. EPR touched on how it was impossible to have a local, non-hidden variable theory to explain the entanglement effect, just by pure common sense. Without hidden variables, how could the particles always show complementary results without communicating? And now Bell's tests have shown that it is impossible for a local, hidden variable theory to explain the entanglement effect. Hence, we can completely rule out locality, but not necessarily hidden variables. In fact, a branch of quantum mechanics called Bohmian mechanics makes use of non-local hidden variables, but we won't go into that now. Which means that quantum mechanics may well be incomplete, but just not in the way that Einstein hoped it would be, not in the way that gets rid of the spookiness. However, it's not all too spooky. For one thing, quantum non-locality does not imply faster-than-light communication because the observations are random. Augustus can't convey any messages to Bob, and if he changes the orientation of his detector, Bob won't notice until they meet up afterwards to talk about the experiment. At least this would have made Einstein happy. The entanglement effect is also really useful in quantum computing, quantum cryptography, and quantum teleportation. It is still pretty spooky though, because the concept of locality has been so fundamental to all of physics, even to Einstein and his theories of relativity, and thus to our understanding of the universe up until quantum theory. Basically, the underlying reality of who you are is quantum, but the macroscopic you and the way you process the world is classical. What the EPR paradox and its resolution did was to show that the underlying quantum reality is non-local, like being made up of complex numbers, whereas you see yourself as local, like being made of real numbers. Hence, at a fundamental level, you do not exist as you. You don't have any local reality. From a macroscopic perspective, your brain is thinking, so you are in existence, surely. But you cannot justifiably say that you exist where you do when you point to yourself, because at the most fundamental level, you just don't. Anyway, that just about wraps up the EPR paradox. I think we'll leave it there to give us adequate time to contemplate our existence as individuals, or lack thereof.